talking a little bit about proteins because they are essential for all forms of life that we know. Think about a statement or assumption that we often encounter, the presumption that wherever there's life in the universe, well, there's bound to eventually be life there also. That all sounds really, really easy. Surprising people can't do that in their bathtubs. What I'm going to do is talk today about this one ingredient, indispensable ingredient found throughout life, proteins. This is important because if these things don't arise naturally, then we have to reflect on the acceptable methodologies used in science. We can't ignore something very, very fundamental and then base a foundation of research on the wrong foundation. So all proteins depend upon them. We need a large number of different kinds of proteins. And many members of each kind. There are thousands of unrelated families of proteins, unrelated structurally in biology, thousands. But proteins are real. You find, basically, most people would categorize them in 3 categories. We have the fibrous types that are really tough, using nails and hair and stuff, tendons. Membrane proteins are typically sensors, receptors, or channels to allow various materials in and out. The best known are the globular proteins. They're easier to study. You can do X-ray or NMR structures on them. So your enzymes, your molecular machines, all the really cool stuff, these are all built upon these globular proteins. Enzymes are important. They accelerate a chemical reaction in the cell, typically by at least a factor of 1,000, more typically a factor of 1,000,000 on up, and there are some really, really dramatic cases like 10 to 15. Now, it is commonly believed there is no chemical reaction in the cell that is not accelerated by some enzyme. That's why I have so many of them. And a lot of the chemical reactions that we have to have in cells would not occur in thousands or millions of years simply fast enough to be of any value to the cell. So you've got a lot of things going on, different metabolic processes, and things simply have to be accelerated. And so you've got anywhere from 1 to 4,000 enzymes are the best guess in animal cells. And these enzymes are mostly based or built upon with proteins. So DNA polymerases, ribosomes, spliceosomes, all kinds of molecular machines, just like big, complicated collections of proteins working together. I think I mentioned the talk before, spliceosomes use about 200 proteins working together. Sometimes multiple copies are necessary of these 200 kinds of proteins. So proteins are really, really important. Without that, we would see no life as we know it. They don't arise naturally all by themselves. And as I said, we need many of them. Many of them, they have to be correct. Not any old polymer is going to work. They have to be in the right proportions in the same place and time altogether. Now, because living systems are so dynamic, the changed environments, context, nutritional needs, interactions, good and bad with other species, which proteins are necessary and how many changes all the time, and therefore they have to be generated and degraded dynamically according to need. So the whole thing is pretty complex. So what is a protein? They're long chains of amino acids, commonly abbreviated AA. So an amino acid has this structure here. Basically, everything here is the same except for this R group, a side chain. So an amino acid has 2 key parts. One is the carboxyl group and the other the amino group at the other end. What happens is the carboxyl and amino group, the two regions interact chemically, spit out water, and then form a bond here. So this happens then in the other direction. The carboxyl group again comes into contact with an amino group from another amino acid, and it forms another bond, and it forms a nice long chain. So typically, well, not typically, on average, about 300 of these amino acids are used to form the chains. And that's independent whether it's bacteria or people. The genetic code codes for 20 amino acids. That means you've got 20 different kinds of side chains that are present on these amino acids. After these chains form, then other chemical things can happen. You know, sugars and other ligands, other things can happen to these long chains afterwards. So the genetic code basically specifies which amino acid is to be attached to the preceding amino acid in a growing chain. These are natural biological amino acids, and each one of them have different properties. Some of them are very basic, some are acidic, some are polar, nonpolar. And the really cool thing is they have different properties, okay? They're slightly different in size, electronic distribution, different chemical features. And what happens then is, depending on which amino acids are located close to other ones, you end up with some really, really interesting chemistry. And that's how you can then create enzymes, which are catalysts, or structural materials, long fibers, and things like that. So the action, the exciting thing, comes from the side chains that are attached to the amino acids. Now, proteins don't form on their own. And the two issues here that a hardcore materialist is facing. The first one is, how could a protein-based life get started at all? And then assuming some of it did happen, where would all of the hundreds of thousands of new kinds of proteins come from afterwards? Today we only have time to look at the first one and just a couple of interesting comments about the second one. Some of you will recognize, I hope, some of the issues, the chemical issues that I'll be introducing. And since I'm an organic chemist, I will bring up a few issues that I suspect aren't known. And I think this will help us to understand the enormity of the problem you have if you want to be an atheist and you don't want to believe that something guided and organized all of this. So in the talk, to keep things very simple, we'll limit ourselves to the globular proteins. This is an example of a fairly typical size globular protein. Globular, you know, it just have a three-dimensional glob sort of shape. It's not flat, it's not long. It's, you know, it's kind of round-like. And what we're going to talk about are three kinds of constraints that have to be met in order. Primary constraints, secondary and tertiary constraints. All these are necessary before something can become a protein. And basically, when you understand all of this, what you realize is, to believe this happened by itself is indistinguishable from a nature. If you want to, from a miracle. If you want to believe that a cell phone just sort of fell out of the sky, you can, but that is no different than a miracle. And that's the point I'm trying to illustrate right now. So, what are primary structures? This is the first requirement that must be met before amino acids can begin the process of producing a protein. So here we see an example of different amino acids that are linked together in a, what looks like a fairly linear structure in the beginning phase of forming a protein. So now, amino acids. Amino acids in their natural state, if you have a microscope and you find an amino acid laying around the ground somewhere, they're solids. They're just totally unreactive. In fact, if you warm them up to sort of make them a fluid, many of them, most of them have very high melting points, so high that many can't even be, you can't even measure the melting point. That's like table salt. They just decompose before you can even get a melting point. These kinds of things don't react. You don't find like sand on a beach and look at it and it just produces a chemical reaction. That's not the way it works. So you need a solvent that gives them mobility and things like that. So that brings us now to the first issue. Polymerization, meaning that these amino acids began to form this what's called a condensation reaction, that the bond forms between the nitrogen and the carbon here, okay? This is unfavorable in water, which is actually otherwise a pretty interesting solvent for these purposes. It's a simple chemical fact that the reaction can go in both directions. That means once you've got a bond formed here, water could be added and split up that chain into two parts, the two amino acids. So if you have a lot of water floating around, like an ocean, a permeable ocean, and a few molecules of amino acid, then the chemistry is going the wrong direction. And this is easily measurable in the laboratory, and everybody knows this. You don't get big polymers forming by themselves in water, by themselves. You can, of course, if you're a clever chemist, by using very high concentrations, all kinds of tricks, so that, get some of these things to polymerize for a while and then quickly isolate them so there's no water around to mess things up again. But this does not happen naturally. So that is now the first thing to remember. These things are very, very unreactive, and putting in water seems like a good idea because there has to be a solvent, but you don't get the chains that you need this way. You don't have pools of pure amino acids being formed somewhere in the same location, whether it's Darwin's warm pool. You don't have anything like you would need or have in a laboratory or a cell. Amino acids, incidentally, are manufactured by the cells. They take raw materials from other sources, and they manufacture the amino acids that are needed. These things are not just available freely. And keep in mind that these things have a lot of functional groups. The side chain have all kinds of interesting parts to them. You've got the carbonyl part, the hydroxyl part. There are all kinds of other chemical substances can also interact and mess things up badly. So you don't have in free nature a bunch of nice, well-behaved amino acids floating around to create proteins. It's just not true. So keep that in mind. All the experiments show that in anything resembling a natural world or conditions, amino acids just don't react in water. So a couple more things to keep in mind. Here's an example of a couple of amino acids. This part here, this is the same for the 20 amino acids of interest in nature. It's the same. And they got the side chain. Look at the side chain here. You've got another amino group, just like here. Look at this side chain here. You've got a carboxyl group, just like here. And that is bad. Bad under natural conditions because this could react with the wrong carbonyl somewhere else, or this amino could react with the wrong, for example, this could react with this, or this amino could react with that. And remember, if you need hundreds of these amino acids reacting only in the linear form, you're going to get a mixture of all kinds of garbage. Incidentally, this is what happens also if instead of using water, you were to heat them up. Let's say you're a really, really imaginative evolutionist and you want to propose these amino acids fall in the neighborhood of a volcano where it's really, really hot, maybe some lava stones. What happens is you get a huge mixture of chemistry. All the side groups here are doing all kinds of wicked things. And everybody knows, all chemists know, what you end up with are three-dimensional tar. It's just gunk. So you got side chains now that can react. And you have another problem, that is what we call the intramolecular reaction. Here you got an amino acid, and here you have another one. Now, what you want to happen, or what nature would like, is for the carboxyl group here to interact with amino group, and then, again, continue in a straight line. What happens instead, if you just put the things together and stir them up in the laboratory, is as soon as this bonds here, these two amino acids are held close together, very close, very convenient, so that this amino group will quickly discover in its immediate neighborhood a carboxyl group, and it forms a cyclic structure. This is what happens. It doesn't just ignore what it could easily do and form a bond here and wait around for a few thousand years until another amino acid comes floating by and decides, as a well-behaved growing protein, delusions of grandeur, to form a nice chain. That's not what happens. And this is what the experiments all show. You don't get long chains, you get all these cyclic products. So you've got already a massive problem. Say that you somehow have started to produce a linear chain. That means that the stuff we just talked about somehow occurred. Those are the primary constraints. Now we have to talk about secondary structures. We're still far, far away from having a protein. Secondary structures are special things that happen if you get the right amino acids together in a sequence. Two very important structures are alpha helixes. This kind of structure here. These are amino acids, okay? And you get several of them in a row, and it forms kind of like a cycle here. And the other one are these beta sheets, so kind of flat like ribbons. So for chemical reasons, if you have the right amino acids together, they form these structures. And that's good because instead of having big random chains, polymers, you have certain structure that are very useful. And you also have something called turns. I'll mention that in a couple of minutes. Now, you've heard, I'm sure, that we have two forms of amino acids, the D and the L. And they have to be optically pure. In biology, the L form is used only. And the reason for that is because otherwise you can't get these secondary structures. These are the two kinds of amino acids. They're mirror images. You cannot superimpose them on each other. You have to break a bond to the central carbon and reattach it on the other side to then get the other one. So they are mirror images. We say left and right-handed, and they are different. And you do have to have all in either the L or the D form. And we see in biology they're all the L form, so that you get the sort of regularity that is necessary. Otherwise, it will not be able to form the kinds of bonds necessary and create a random structure. So that's why these things have to be optically pure, and very few combinations of amino acids. You can't just string them together in any old order. Only certain combinations lead to these two kinds of structures. So these are the kinds of problems now that we face in creating proteins. Here, a picture that shows, if you have a little patience, a little more exact what happens. These things sort of coil in this direction, and this carbonyl here forms a hydrogen bond with this hydrogen here. And if you spend a little time learning chemistry, then it becomes obvious why you can't have a mixture of D and L, because you don't have this sort of regularity that would form. So, and this is now a picture of the beta sheets. It comes in two flavors, parallel or anti-parallel. You don't have to understand this in depth. All you have to remember is that you cannot get these secondary structures if you have a mixture of D and L amino acids. And even if you did have only the pure L form, you still need a very, very small subset of the right sequences of amino acids to get these kinds of structures. The turns are just the portions of the polymer that are linked between these alpha coils and beta sheets. And here's where a lot of the chemical and biological things happen. But once again, there's a lot of structure here, the different kinds of features, hairpins, other stuff that occur here. And once again, you have to have the L form, or these structures here are unpredictable and unreliable, and they don't have the specificity that you need. And finally, you've got the tertiary structures. That means the first two set of requirements have been met, and now what you want to do is have things fold in a very predictable, low energy state to produce a proper globular protein. So that can only happen if these secondary structures are in specific locations, and then other chemical features of these side chains from amino acids then contribute. They can form the disulfide bridges and hydrogen bonds and all kinds of electrostatic, especially a combination of hydrophobic, hydrophilic interactions that keep water out, and the hydrophobic parts sort of nice and close together. And all these sort of interactions together allow a stable form to occur. The bad thing is when these chains form, they are unstructured, and they can fold and crumple up in a quadrillion ways, all of them wrong. So it's a very, very fascinating exercise, and it's still not properly understood how this folding occurs in real proteins so effectively and so quickly. But the bottom line is the average protein, globular protein, has a very stable and very reliable tertiary structure. And then we won't talk about the quaternary structures. This is where different proteins together interact then to do something useful. A few more comments to give you a better picture of what's going on here. Scientists have tried to estimate what proportion of random amino acid sequences, when they polymerize, would actually produce a stable structure. And most experiments use very, very small proteins, first of all, because nothing else works, and it's easy to analyze. Keep in mind what that really means. Let's say that this is a small part of a protein, that's the second part, that's the third part. If there's a certain probability that this part will fold properly, and this, then getting a protein with all three means a probability that is at best the probability of each individual unfolding properly. I say at best because then in addition they can sort of interfere with each other and mess things up in addition. So whenever you read about people saying they did some experiments and they make an estimate of whatever numbers they come up with, let's look at the size of the amino acid. If it's, for example, 100, keep in mind that the average has 300 amino acids. So right away, take whatever number they are giving you and say raise to the third power. So when you look at some of the estimates that have been published, actually from the Intelligent Design, Sauer from Michigan, who's definitely not in the Intelligent Design group, when you extrapolate the size of the proteins they studied, axis was about 200 amino acids, just to have a common denominator. These are the kinds of numbers you're coming up with. That means that if you had 10 to the 151 random chains, one of them may fold properly. So getting a chain to fold properly is very, very unlikely. This is, again, ignoring everything else, ignoring the fact that you have the D and L forms, ignoring the fact that these things don't polymerize in water by themselves. You're ignoring all that. You're just saying somehow you've got a long chain of about 300 amino acids, and you have a whole bunch of them. How many of them would even fold properly to be reliable and useful for biological purposes? So the number is not known. Of course, evolutionists would like you to believe that the number is very low. All the evidence shows the opposite. I did an extensive review of the literature, did not find a single example of a chain having been produced by chance and having been shown to fold properly, not a single example. So what I can say is, based on everything that I've studied, since nothing has been found, and based on the number of attempts that were made, the number's got to be lower than that, 10 to the 11th. And these are all for very, very, very small chains. Therefore, I would say, as a rule of thumb, for an average size protein, you're talking about 1 out of 10 to 33, and the number is probably lower than that. So these are very, very unlikely things. So then what we have concluded. First of all, linear chains aren't going to form at all in free nature. They hydrolyze instead of polymerizing. You've got the side chains doing bad things. Let's look at the D and L requirement. If you have a 50-50 chance of having a L like you would like, and you need 300 of them, then you'd have a probability of 0.5 times 0.5 times 0.5 times. That is a very, very small number. To put things in perspective, if the entire Earth was composed of nothing but these amino acids, for that size chain, then you would have a possibility of about so many chains, about 10 to 47. Again, you need solvents and everything else. But you see that this number is grotesquely too small compared to the number of attempts you would need to produce just one linear chain by chance that would be optically pure, as all modern proteins are. So you have no way of even getting started. And that is just the first step, the primary structure only. And then I've already mentioned the kinds of probabilities that we're looking at for tertiary structures. Really, really bad. Of course, somebody really clever could say, well, wouldn't things be a little bit easier if instead of using 300 amino acids, evolution got started a long time ago with much smaller proteins. My message to you is, be careful of these arguments. They're all wrong. It goes a little bit back to the previous talk by Sal. You got trade-offs. You're exchanging here one problem by another problem. A protein is multifunctional. That means different parts of a protein is used for different purposes. This part could be used, to signal where it's to go. This part binds to another protein. This one part binds to another protein. This one has an enzymatic reaction occurring in this pocket. A protein does many things, and that's large. So simply saying starting with a smaller protein is creating additional problems. For example, let's say you have very, very small proteins. We now need far more to do the job that you're doing before with humans. You would need proteins to hold the two small things together. Before, a large surface of the protein could interact with another protein and be held together. If both are small, you now need a third protein that just happens to be able to fit both ends together. So it goes back to my argument. If the probability for a small part of a protein is certain, you've got 2 or 3 other probabilities to meet, you multiply them all together. Then it applies here. Facetious to say, instead of needing 2 large proteins, now you just say we have probability, but unfortunately need more of them. You can actually gain. And maybe a couple more comments. Keep in mind that to start off with very small proteins introduces many other problems. It would unfold. It would not be folded state. For that, you do need a large number of interactions to keep things together. For these proteins, stay stable long enough even in the water of a cell, because it holds itself together strongly enough and has on the outside parts that repel water. This would not be true of very small proteins. And in addition, because tiny protoproteins can't hold itself together strongly, it would be far easier then to react with all the wrong surface. So it is simply not correct to do what people are doing. They're saying evolution started simple long ago. Proteins are much smaller. All they're doing is exchanging one unlikelihood by a different unlikelihood. Just having a bunch of folded proteins still won't do any good biologically. You've got to have the right kind at the right time in the right environment in the right proportions. Some of the kinds of things that proteins are used for everywhere in nature, ribosomes, all cells, all bacteria, everything needs ribosomes. The simplest one known require more than 50 kinds of proteins. The citric acid cycle, again, not easy. It needs a whole bunch of enzymes. So all the examples that we know that are found everywhere in nature already require a large number of proteins. Keep that in mind. I'm saying that forming a linear structure is extremely unlikely in nature. If it did happen, getting a folded structure is extraordinarily unlikely in addition, and now I'm saying you've got to have a whole bunch of them. Well, just multiply those unlikelihood by the number of proteins. If I tell you the number is something like 10 to 33 for 1, well, just raise that to the power of the number you need. If you need 50 together for ribosome, then the number's got to be lent to the 30 power raised to 50th power. These are the kinds of things we're talking about, okay? So if you want to be a naturalist, just say it right away you believe in miracles. The final thing, I don't have time to go into that. Even if this were to sound like it started, you have all kinds of additional things, problems, before an evolutionary story can be true. Let me give you a couple of things that I don't think people know. For example, if you had a small, simple organism, it would reproduce fast. To become more complex, to gain a larger genome, it would have a problem. For example, it would take longer to reproduce. The DNA copying time would take longer, and all of this would be a disadvantage. It would be out-reproduced by the streamlined genome. The streamlined smaller genome would require fewer resources, less DNA, fewer proteins, less energy, less raw materials. It would simply have all of the advantages. So all the trend in nature is towards simplification. Bacteria can lose DNA they don't need that allows that species to reproduce faster. So trend is not towards more complexity. More DNA requirements mean more errors. And that would lead to a cascade. If you have more and more errors in that particular lineage, it would just become worse and worse with every generation. And this is true, by the way, also for translation and transcription. If your proteins get larger and larger, then you end up with more and more errors per protein. And proteins are very, very sticky. They interact together. They misfold. They create chaos. The last thing you want are a bunch of mistranslated proteins. And finally, I mentioned there were thousands of unrelated families, structures. For example, here you have a certain family that consists only of alpha coils. You have another family of proteins that's based on beta coils. Typically, things are logically and from sequence very, very, very far apart. You need a large number of these. You need many hundreds of kinds of proteins. So you have a huge issue here trying to explain how these could have arisen. So the conclusion, these things don't happen by themselves. There's a lot of speculation. There's a lot of nonsense about the RNA world. I can't go into all the reasons why that's foolish, but it doesn't even begin to address what I'm talking about here. Since people can't explain the source of DNA or proteins, you invent an RNA world. Well, now you have two problems. You've got to explain how that arose, and then the transition into all these proteins and genes. So in a sense, you're just ignoring the problem. These things they don't produce themselves freely in nature. But to increase in sophistication, somehow you would have to have more and more of these things. So it's just this compulsive demand for a naturalist explanation that's getting science into trouble. Because of that, you're forced to bad theories because you're limited to natural law and to randomness, even though it doesn't make any sense. Okay, I'm done.
This is John Calvert. Can you hear me?
Yes, John, I can hear you.
Okay, my question is, have you had a chance to review Andre Wagner's Arrival of the Fittest?
Yes.
And I'm trying to wade through that book now, and it just totally is, I can't understand at all his theory. It seems to be a self-organization theory, and it's difficult for me to figure out a way to punch holes in it other than it just is, it seems silly.
He's already starting that life exists. He's not addressing any of the issues of the origin of the genes and everything else. He is looking at the question of increased sophistication and complexity. So he goes into things like rewiring genetic circuits and stuff like that. They're just the short story. Again, it's a separate topic, but the short answer, and there are two things to keep in mind. The first one is any sort of genetic recircuitry. For example, when organisms develop and different cell types are created, this is informationally guided. These things don't happen by chance. So in that respect, what he's saying is interesting and true. There is something that is reorganizing how different genes act together. That is one. The other is not true, in that he is oversimplifying how easy some of the things would happen by themselves. He's ignoring all the things that can go wrong.
Okay, thanks.
Royal, can I ask a question?
Of course.
Yeah, your response just then, plus another thing you said earlier in the talk, seems to kind of reinforce something. Maybe you can tell me if you agree with this or not, and that is that when you're dealing with systems like you said with the proteins, how difficult it is to explain naturalistically, when there are methodologically naturalistic friends raise up alternative theories, raise up alternative responses to say, hey, well, let's try this, or let's try this, or let's try some other suggestion. Oftentimes what you're saying is they may increase the probabilities, but they have left out other factors that may cancel out those increased in probabilities. The way I used it in my talk was about costs, like we can save money if we do this, but then what they might be missing, and what we want to ask them questions is, have they missed something in which either the probability actually goes back down again, or which the money that you've saved you actually have to pay over here. So that's kind of a strategy that we should be looking out for, is to try to find these alternative ways in which they're missing some of the other side of the ledger, so to speak. Is that what you're saying? Would that be a good strategy to keep that in mind?
Yeah, that is correct. Everything you're saying is correct. I don't know if it ties in directly to my talk. What was happening is they're looking for contrived scenarios to get around how nature normally would work. What they're really doing, and mathematically, is you can show this, is they're adding information. If somebody says, look, it's not as bad as you guys say. We're going to take a simplified cell, we're going to remove a bunch of genes, deactivate them, and we're going to show you that these things can survive on only 700 genes, and things work real well. look more carefully at experiments. You know, they're feeding in the nutrients so they no longer have to process their own stuff. They're keeping temperature just right. In other words, they have designed elements to compensate for what cannot happen by itself. And
Right.
it's not serious.
So they're
Uh,
smuggling. They're
yes,
secretly smuggling in some things.
exactly.
Yeah.
This happens all the time. It's all the time. It's a long story. We can talk about this. That would be worth a whole conference, what's happening. But just to point you in the right direction, because I know you've got a background in information theory and that kind of thing. If you're looking at outcomes, how would something behave naturally? You've got coded messages that are guiding behavior, but you can smuggle in things that would also ensure the outcome. If you run a coin down a funnel and then put that funnel where it's supposed to land, you'll smuggle in information that doesn't have to be communicated by instructions. This is what's happening with experiments.